So for this demonstration, we're going to be looking at momentum of objects during collisions. And what I've got rigged up here is this track has two photo gates on it. And the photo gates are set up so that when an object passes through the first photo gate, it will start my clock. And when an object passes through the second photo gate, it'll stop the clock. So we've got time being measured of how much time does it take for an object to go from one photo gate to the other. The distance between those photo gates is approximately half a meter, but we're only going to be seeing time. If you wanted to, you could calculate the speed that the object is moving from one photo gate to the other by taking the distance between them and dividing it by time. But for this demonstration, we're just going to leave it as time and talk about what that must mean. So remember, the bigger the time number is, the slower the object is moving because it takes more time to go from photo gate 1 to photo gate 2. The opposite is also true. The smaller the time, the faster the object must be moving. So for this demo, I'm going to start off. I have a spot marked on our track, and I'm going to release one cart by itself to roll down this hill and through the photo gates. So this is a no collision run, but we're just getting a baseline of how fast will the cart go? How much time will it take to go from one photo gate to the other? 0.41 seconds. So if I roll the cart down the hill by itself, we're going to have a time of 0.41 seconds for it to move from one to the other. For the second demo, what I'm going to do is I'm going to take this second cart, which is exactly the same mass. Well, technically not exactly the same, because we've also attached a spring to this one. And I'm going to have the two carts collide. Because of this spring, we know that we're going to have an elastic collision, where the objects separate and travel apart from each other after the collision. So two objects of identical mass experiencing an elastic collision. Here we go. And what we see is 0.41 seconds again. When the carts collided, the first cart stopped moving and the second cart moved off at a new speed. But it turns out, because these carts are identical and we had a perfectly elastic collision, what happened is all of the momentum from this cart was transferred into the second cart, and so the second cart moved off with the exact same velocity that the first cart had. And we know it's the exact same because it took the same amount of time to go from one photo gate to the other, 0.41 seconds. So that is an elastic collision. The total momentum of our system stayed the same the entire time because however much momentum cart 1 had, we know that that momentum caused it to move at a speed where it took 0.41 seconds to go from one photo gate to the other. And when we had a collision, that same amount of momentum transferred into the second cart. It was all of the momentum. So the first cart stopped moving right where they collided, and the second cart moved off with the same velocity that the first cart originally had, so the same total amount of momentum. Conservation of momentum means that the total momentum of these two carts, the two-cart system, if you will, the total momentum of cart 1 plus cart 2 stays the same until there's some outside force, like for example, cart 2 colliding with our bumper at the end of the track. What I'm going to do for this last trial, I'll reset our clock. I'm going to spin the cart around. So now, instead of having a spring in between the collisions, I have Velcro on both carts so that when they collide, instead of bouncing apart and experiencing an elastic collision, they will stick together and experience an inelastic collision, or a not elastic collision. This is going to be a perfectly inelastic collision, which is also sometimes called a hit and stick collision, because the objects are going to hit and stick together, which we're kind of guaranteeing with our Velcro. So now think about what you would expect to happen. If it takes 0.41 seconds normally for the cart to go from one to the other, and 0.41 seconds during an elastic collision for the cart to go from one to the other, what do you think is going to happen when we have two carts that hit and stick together going from one side to the other? Let's find out. So we saw that it was 0.87 seconds, which is obviously more. In fact, it's more than double what it was before. In a perfect world, what we might expect is that because we've doubled the mass of the two carts, we might expect that we would get exactly half the velocity, which would give us exactly 2 times the time. It was a little bit off, and that could be for multiple reasons, including the spring being slightly more mass on the carts. So an inelastic collision, where the two objects hit and stick together, the momentum is still conserved, but the velocity is significantly different. And that's because that same amount of momentum that it had at the beginning is now being spread and shared between two different carts. And so instead of getting exactly the same velocity as the first cart, we're getting half the velocity, because there's still the same total momentum, but twice as much mass. We can only have half the velocity for the inelastic collision, because that momentum is being shared between two objects instead of being only in one cart.
Yeah. Do the elastic one more. I'm going to do slow-mo so we can see if the spring compresses enough.
Okay.
If you don't mind.
Yeah. Here we go.
Yeah.